In today's lesson, you will find out what is meant by a pair of complex conjugates, and you will be able to use conjugates to divide complex numbers. In your notebooks, please. Every complex number has a complex conjugate. A complex conjugate is the same as the complex number, but with the opposite sign on the imaginary part. Let's take a look. If we have z equal to 5 plus 3i, then its conjugate, denoted by z star, is equal to 5 minus 3i. We can then take a look at what would happen if we added a complex number and its conjugate, or multiplied a complex number and its conjugate. Let's take a look at both of these. Z plus Z star, adding these two together, gives us 10. And Z multiplied by Z star, when simplified, gives us 34. You'll notice that both of these are real, and this is true for all pairs of complex numbers and its complex conjugate. The sum and the product of a complex number and its complex conjugate is always real. Let's take a look at an example that involves division. 2 minus I divided by 5 plus 3i. We know that if we multiply a complex number by its conjugate, we will get a real number. And in order to divide complex numbers, we need to change the denominator into a real number. So we must multiply it by its conjugate. But we don't want to change the value of the question that we start with. In order to do this, we need to make sure that the numerator and the denominator are the same. So both of these will be the complex conjugate of the denominator of the question. Multiplying these out and simplifying as we go, we can then write the complex number with a real and an imaginary part. So 2 minus I over 5 plus 3i can be written as 7 over 34 subtract 11 over 34i. Now it's your turn. Stop the PowerPoint here before I look at some of the solutions to these questions. Remember, if you're looking for a little hint, for the first one there, 3 plus 2i over 2 plus 4i, you need to multiply top and bottom by the conjugate of the denominator, so 2 minus 4i and 2 minus 4i. Okay, running through those answers then. I'll demonstrate some of the solutions on the next page. Okay, I've chosen to have a look at A, C and F. First one, if we multiply through by the complex conjugate of the denominator, so 2 minus 4i over 2 minus 4i, multiplying the numerators together will give us 6 minus 12i plus 4i minus 8i squared, and that will be over 4 minus 8i plus 8i and subtracts 16i squared. Substituting in minus 1 for I squared is 6 minus 12i plus 4i and plus 8, and that is over 4 minus 8i plus 8i plus 16, which simplifies to 14 minus 8i over 20, which reduces to 7 minus 4i over 10. And then both of these two components can be separated out. Next one, multiplying through by 6 minus 2i over 6 minus 2i. The numerator, 42 minus 14i, all over 36 minus 12i plus 12i minus 4i squared, and substituting in the denominator there, 36. Sure why we're at 13. 36 minus 12i plus 12i. Of course, we could simplify these here, but I'm just going to leave it in full just for now. Plus 4 down at the bottom. This simplifies to 42 minus 14i all over 40, which reduces to 21 minus 7i over 20. And the final one, multiplying by 2 minus 4i over 2 minus 4i. So the numerators, 6 minus 12i plus 12i minus 24i squared all over 4 minus 8i plus 8i minus 16i squared. I'm going to cancel out these here, so that leaves us with 6 minus 24 times minus 1 and 4 minus 16 times minus 1, which is 30 over 20, which is 3 over 2. Now let's take a look at solving simultaneous equations that involve complex numbers. We have two equations, zi plus 4w is equal to 3i minus 6, and 3z take away 1 plus 10i lots of w is equal to 2i plus 12. In the same way that we would try to solve normal algebraic simultaneous equations, we need to get the coefficients of one of the unknowns to be equal. So here, it looks a little bit more simple if we take the z and the z here, so we ensure that the coefficients are equal. And we can do that by multiplying the first equation by 3 and the second equation by I. Let's take a look at the answer there. Multiplying through by 3, so all of those terms, 3zi, 12w, 9i, minus 18. And in the second equation, multiply each of the terms by I. That gives us 3zi minus 1 plus 10i multiplied by wi, minus 2 there, that's come from 2i times by I, so that would give us I squared, which is minus 1, and then 12i at the end. Notice now that the coefficients with z are equal, and therefore we can eliminate that coefficient. If we subtract them, we are left with 2w plus wi is equal to minus 16 minus 3i. Now that would involve multiplying out this bracket here along the way. So just take a little bit of time to think about how you would have got from that step above to this line here. This equation can then be rearranged. So we have w is equal to minus 16 minus 3i all over 2 plus I. And then if we multiply this through by the conjugate of the denominator, this leaves us with minus 7 plus 2i. So it's in a much nicer form. This can then be substituted into one of the original equations. Let's take the first one. Substitute in w for minus 7 plus 2i, rearrange, and we can then divide through by I. Sorry, we don't divide by I, we actually multiply through by I here, otherwise we're going to give ourselves a lot more work. So multiplying each term by I here, and on this side, here and here. So then we have I squared on the left, which is minus 1, that gives us minus z, and on the right hand side we have 22i plus 5. We can then rearrange this, multiplying through by minus 1, so z is equal to minus 5 minus 22i. Please complete exercise 1b on page 8.